It happened on December 26, 2024. Grainy footage began circulating on Chinese social media, showing a massive tailless aircraft roaring over a highway near Chengdu. Drivers pulled over, phones came out. Within hours, the clips were everywhere. The aircraft looked nothing like anything China had officially unveiled before, and that alone was enough to ignite the internet. The design was striking. A huge delta-like wing, no vertical tails, and an unusual 3-engine layout with 2 apparent side intakes, and a 3rd intake buried deep inside the fuselage. Aviation forums lit up almost instantly. Some analysts suggested it could be China's first true 6th-generation combat aircraft. Others argued it might be a long-range strike platform, or even a stealth bomber-fighter hybrid designed for the Pacific theater. Online, the aircraft quickly earned a nickname, the Sky Monster. Almost as fast, it was labeled the J-36, based on a partially visible serial number beginning with 36, seen in some of the footage. It's important to be clear here. J-36 is not an official designation. It's an analyst shorthand, not a confirmed name released by the Chinese military. Chinese state media said nothing. No press release, no triumphant reveal, no carefully edited promotional video. Just silence. And in military aviation, silence has a way of amplifying speculation rather than containing it. Claims began to spiral. Some posts suggested extreme performance figures. Others hinted at advanced drone swarm control or revolutionary stealth capabilities. In the most exaggerated takes, the aircraft was framed as proof that American air dominance was already finished. The lack of official information created a vacuum, and the internet rushed to fill it. But when you step back from the excitement and focus only on what can actually be verified, a very different picture starts to emerge. What we know for certain is that the aircraft is real. Multiple independent sightings and follow-up test flights into 2025 confirm it is not CGI or simulator footage. At the same time, there is no credible evidence that it is operational or even close to entering service. Everything points to an early-stage prototype, and that uncertainty matters because the timing of this sighting is impossible to ignore. While the world was fixated on a mysterious aircraft in the sky, China was in the middle of the most sweeping military anti-corruption purge it has seen in decades. That purge directly targeted the very institutions responsible for building, funding, and fielding advanced weapon systems like this one. So the real question isn't whether the aircraft looks intimidating in low-resolution footage. The real question is whether China's military-industrial system, as it exists today, can reliably transform experimental prototypes into combat-ready platforms. To answer that, we have to slow down, ignore the hype, and look at the fundamentals, the engineering realities, the design trade-offs, and the political and industrial environment behind the imagery. And that starts with the aircraft itself. At first glance, the aircraft looks overwhelming. It is visibly larger than the J-20 and closer in size to aircraft traditionally associated with long-range strike rather than air superiority. That alone should immediately slow down the next F-22 killer narrative. Size in military aviation is never free. Every additional meter of wingspan and fuselage volume comes with trade-offs in weight, signature management, and operational flexibility. The most controversial feature is the reported 3-engine configuration. According to open-source imagery, the aircraft appears to use 2 engines mounted laterally, with a 3rd engine fed by an intake buried deep in the center fuselage. On paper, 3 engines suggest massive thrust and long range. In reality, they introduce some of the hardest problems in stealth aircraft design. Stealth is not just about radar, it is also about infrared and thermal management. Modern low observable aircraft go to extraordinary lengths to hide and cool their exhaust. The F-22 and B-2 use complex exhaust shaping, thermal shielding, and airflow mixing to reduce their heat signature. Adding a 3rd engine creates additional exhaust flow, additional heat, and additional turbulence. Managing that heat without dramatically increasing infrared visibility is extremely difficult, even for countries with decades of experience in stealth design. There is also the issue of internal volume. Fighter aircraft are essentially flying compromises between fuel, weapons, sensors, and engines. In stealth aircraft, those compromises become even more severe because everything important has to be carried internally. Engines require intake ducts, and stealth intake ducts must be long and curved to hide the engine face from radar. A third engine means a third intake duct, and that duct has to run through the very center of the aircraft, exactly where designers normally place internal weapons bays, fuel tanks, and mission avionics. This does not make the design impossible, but it does suggest that the aircraft may be optimized for a very specific role rather than being a universal air superiority fighter. Some analysts believe the size and configuration point toward a long-range strike or command and control role, possibly operating behind friendly lines rather than penetrating heavily defended airspace on its own. The overall shape of the aircraft has also drawn comparisons to earlier Western designs, particularly Northrop's YF-23 from the 1990s. The resemblance is visual rather than technical, but it highlights an important point. Radical-looking aircraft are not automatically new. Many of the design concepts being discussed today were explored decades ago, abandoned not because they were impossible, but because they were too complex, too expensive, or too difficult to maintain at scale. This is why serious analysts are cautious. The existence of a flying prototype tells us that China is experimenting with advanced configurations. It does not tell us that the design is mature, survivable, or suitable for mass production. History is full of experimental aircraft that flew successfully, but never became operational weapons. In other words, the aircraft proves ambition, not capability. To understand whether that ambition can translate into real combat power, we have to look beyond the airframe and into the system that builds it. And that means following the story out of the sky and into the factories, procurement offices, and political machinery behind China's military modernization. That's where the picture becomes far less impressive. While analysts in the West were debating thrust-to-weight ratios and radar cross-sections, something far more consequential was unfolding inside Beijing. Quietly, deliberately, Xi Jinping was dismantling the leadership structure that had overseen China's military modernization for more than a decade. This was not a routine anti-corruption campaign. It was a systemic purge, and it struck directly at the heart of weapons procurement. In late 2023, China abruptly removed Defense Minister Li Shangfu from public view. There was no announcement, no explanation, and no replacement for weeks. When the confirmation finally came, it was clear this was not symbolic. Li was expelled from the Communist Party and placed under investigation for corruption related to equipment development and procurement. That detail matters. Before becoming defense minister, Li Shangfu spent years as head of the Equipment Development Department, the office that approves and oversees every major weapons contract in the People's Liberation Army. Aircraft avionics, engines, missiles, sensors, and entire platforms passed through that system. His removal signaled that procurement decisions were not being made purely on performance or readiness, but on connections, favors, and internal politics. The shockwaves did not stop there. China's rocket force, the elite branch responsible for conventional and nuclear missiles, was effectively decapitated. Its commander and multiple senior officers were removed, followed by the fall of Wei Fenghe, a former defense minister and rocket force veteran. The message was unmistakable. Corruption was not isolated. It was entrenched. Western intelligence assessments and reporting from major outlets described a military struggling with falsified readiness reports, inflated performance claims, and a culture where admitting technical problems was more dangerous than hiding them. The problem wasn't just stolen money. It was systemic dishonesty. By late 2024, the purge widened again. Admiral Miao Hua, head of the PLA's political work department and one of Xi's longtime allies, was suspended. This marked a shift. The campaign was no longer only about corruption. It was now about loyalty, discipline, and control. Entire chains of command were being disrupted in real time. And this is where the J-36 story collides with reality. Advanced aircraft programs do not exist in isolation. They depend on stable leadership, long-term funding, consistent quality control, and procurement systems that reward technical honesty. When generals are being arrested, executives are disappearing, and auditors are crawling through decades of contracts, everything slows down. Decisions are delayed, risks are avoided. No one wants to be the next name on a list. In China's system, this creates a paradox. Xi Jinping is almost certainly correct that corruption weakens military power. In the long term, rooting it out could make the PLA stronger and more reliable. But in the short term, the next several years, it creates paralysis. Officers become cautious, contractors hesitate, programs lose momentum. This matters because experimental aircraft do not become operational by accident. They require relentless iteration, constant feedback, and the willingness to admit failure early and often. A system gripped by fear is the worst possible environment for cutting-edge aerospace development. So when we see a dramatic flyby of a mysterious prototype, we have to ask a harder question. Not can China design bold aircraft? Clearly, it can. The real question is whether the institutions responsible for turning prototypes into dependable weapons are currently functional. To answer that, we have to look even deeper, not just at the generals, but at the corporations that actually build China's military aircraft. And that leads us straight into the Aviation Industry Corporation of China. If the purge of generals shook the command structure, the investigation into China's aviation industry struck at the foundation. Because no matter how ambitious a design looks on paper, aircraft are not built by slogans or flybys. They are built by corporations. And in China, that means one entity above all others. The Aviation Industry Corporation of China, known as AVIC, is a state-owned monopoly that dominates the country's aerospace sector. Chengdu Aircraft, which builds the J-20 and the new prototype seen in 2024. Shenyang Aircraft, responsible for carrier-based fighters. Engine manufacturers, avionics firms, materials labs, all of them ultimately sit under AVIC's umbrella. If it flies in military service, AVIC touched it. That is why what happened next mattered so much. In 2025, Chinese authorities formally indicted Tan Rusong, AVIC's former chairman, on charges ranging from bribery and embezzlement to insider trading and leaking confidential information. State media described him as someone who had been living off the military, a phrase reserved for cases where defense spending becomes a personal revenue stream rather than a national priority. Under Tan's leadership, AVIC did not behave like a traditional defense contractor. It increasingly functioned like a financial conglomerate. Its investment arm, AVIC Capital, expanded aggressively into stock speculation, using defense programs to attract investment and inflate valuations. New aircraft concepts, engine upgrades, and modernization announcements became tools to boost share prices rather than milestones tied to operational readiness. This matters because hype is cheap, but engineering is not. A stealth aircraft program is a long, grinding process filled with setbacks, delays, and expensive failures. When success is measured by market excitement instead of fielded capability, incentives shift, problems get hidden, schedules get massaged, prototype success is exaggerated while manufacturing challenges are buried. Then the purge hit. As investigators moved through AVIC's leadership, procurement approvals slowed to a crawl. Contracts were frozen. Executives hesitated to sign off on new programs, knowing that any decision could be re-examined months later under a political microscope. Engineers still went to work, but the system around them locked up. The financial impact was immediate. While Western defense contractors saw rising revenues driven by global conflicts and rearmament, AVIC's reported revenue declined. That drop wasn't about lack of demand. It was about institutional paralysis. Money existed, but no one wanted to touch it. This is the environment in which the J-36 prototype emerged. Seen in this light, the aircraft looks less like a polished weapon and more like a proof of ambition, something that could be shown without requiring the full commitment of serial production, supply chain stability, and long-term sustainment. A flying demonstrator is politically useful. It signals progress without demanding accountability for follow-through. And that distinction matters. History is filled with impressive prototypes that never survived the transition to operational reality. The difference between a technology demonstrator and a combat aircraft is not how it looks in the sky, but whether the system behind it can support years of refinement, testing, and mass production. Right now, that system is under investigation, and even if corruption had not disrupted AVIC's leadership, there remains a deeper problem, one that no amount of financial restructuring can easily solve. A problem that sits at the very heart of modern air combat: the engine. Every modern combat aircraft is ultimately defined by its engine. Stealth, sensors, And weapons mean very little if propulsion cannot deliver reliable thrust, efficiency, and thermal control. For China's next-generation ambitions, that engine is supposed to be the WS-15. The WS-15 is intended to replace the older WS-10 series and finally give China an indigenous power plant capable of sustained high thrust and, potentially, supercruise. It is designed to do what the American F-119 engine did for the F-22 decades earlier: combine raw power with reliability, durability, and manageable maintenance cycles. On paper, it is exactly what an aircraft like the J-20 and any future platform larger and heavier than it would need. But engines are where aerospace programs go to die. Developing a high-performance turbofan is one of the most demanding industrial challenges in existence. The tolerances are microscopic. The temperatures are extreme. The materials involved push the limits of metallurgy. Even small inconsistencies in manufacturing can lead to catastrophic failure. This is not a problem you solve with one successful test. You solve it by repeating the same process thousands of times, with near-perfect consistency. China has made real progress here, but progress is not the same as mastery. Open-source reporting and defense analysis indicate that the WS-15 has entered limited service and testing, but not at the scale originally envisioned. Many J-20s continue to fly with upgraded WS-10 variants, which are reliable but do not deliver the same thrust-to-weight performance expected from a true next-generation engine. That gap matters, especially for larger airframes with greater fuel loads and payload demands. At the heart of the issue are high-pressure turbine blades. These components operate at temperatures that exceed the melting point of the metal itself. To survive, they rely on advanced cooling channels and single-crystal casting techniques that eliminate internal grain boundaries. Producing these blades is not just about knowing the process. It is about executing it flawlessly, over and over again. At industrial scale, China can produce these blades in controlled environments. The challenge has been consistency. Reports over the past decade have pointed to uneven quality control, low production yields, and engines that meet performance targets on test stands, but struggle to sustain them across long service lives. These are not unique problems. Every major engine program has faced them, but they become far more dangerous when combined with corruption and schedule pressure. When procurement systems reward speed over durability, shortcuts appear. Materials are substituted. Inspection steps are reduced. Failures are quietly reclassified. The result is an engine that technically works, but only within narrow margins. That may be acceptable for a limited fleet. It is unacceptable for a large force expected to operate in high-tempo combat. This is where the J-36 narrative begins to strain credibility. A larger, heavier aircraft with 3 engines would place even greater demands on propulsion. If the WS-15 has not yet fully stabilized in service on the J-20, fielding a more complex platform would require a level of manufacturing confidence that China has not publicly demonstrated. None of this means the WS-15 is a failure. It means it is still maturing. But in military aviation, timing matters. An engine that is promising in a laboratory does not win wars. An engine that can be built, maintained, and trusted by frontline units does. And propulsion is only one half of the survivability equation. Even a powerful aircraft becomes vulnerable if it cannot remain unseen. Which brings us to the skin. Stealth is the signature of modern air combat, but it is also one of the most fragile and unforgiving aspects of aircraft design. Radar-absorbing material, or RAM, is not a magical skin you can simply paint on and forget. It is a complex chemical coating that must adhere perfectly to the airframe, survive extreme temperatures, resist corrosion, and maintain its shape under the stresses of supersonic flight. Even the United States struggles with it. F-22s, for instance, often require extensive maintenance to repair peeling coatings after months of operation. China faces a unique challenge. The humid, salty air of the South China Sea is particularly aggressive toward coatings, accelerating degradation and corrosion. Reports on the J-20, the PLA's current stealth fighter, suggest that the RAM can begin to delaminate after just a few months of regular use. Maintaining these coatings is time-consuming, expensive, and technically demanding. not something that can be solved through propaganda or clever marketing. Chinese state media has often emphasized breakthroughs in materials science, citing structures inspired by natural textures or ancient weaving techniques. While these reports make for impressive headlines, they do not provide independent verification of operationally durable stealth materials. The reality is that any aircraft, no matter how advanced, is only as stealthy as its weakest surface. A large prototype with peeling or inconsistent coatings is not a ghost in the radar. It is a visible target, especially to modern infrared and radar sensors. For a theoretical aircraft like the J-36, this is a major hurdle. Its larger surface area magnifies the consequences of imperfect RAM. Even minor flaws on a wing or fuselage could make the aircraft highly visible to enemy systems. Add to this the complexity of maintaining 3 engines, each producing additional heat, and the challenge of true low observability becomes even greater. In short, stealth is not just a design feature. It is a continuous process of material science, precision engineering, and operational maintenance. An aircraft may look futuristic in footage or digital renders, but if it cannot sustain its low observable characteristics in real conditions, its tactical advantage evaporates. Understanding these limitations brings us back to the bigger picture. The J-36 prototype is undeniably impressive to watch in the sky. But when we consider the combination of engine maturity, stealth maintenance, and the political paralysis caused by Xi's Purge, the reality becomes clear. Prototypes can fly, but operational capability is far more elusive. Which leads us to the final question. What does all this mean for China's military power in the Pacific? And how does it compare to the United States' own next-generation programs? By now, the picture is clearer. The J-36 prototype, the so-called Sky Monster, is real, but its existence does not automatically translate into battlefield dominance. The United States is developing the Next Generation Air Dominance Program, NGAD, a family of systems rather than just a single aircraft. NGAD combines a manned fighter with autonomous loyal wingman drones, connected through secure, resilient networks. The pilot provides intent, while AI handles much of the tactical execution. It is designed to operate under real-world combat conditions, where reliability, maintainability, and network lethality are paramount. The J-36 rumors suggest a different approach. Some images appear to show a side-by-side cockpit, which implies a reliance on a human operator to manage complex systems that NGAD would automate. That configuration could indicate that China's autonomy and AI systems are not yet trusted to handle mission-critical operations on their own. A second human in the cockpit is a workaround, not a technological leap. Quantity is another factor. The J-20 is dangerous primarily because of numbers. China has been producing them rapidly, and sheer volume can be a form of deterrence. But quantity means little if maintenance is inconsistent, engines fail, or stealth coatings peel off. Reports of operational delays, limited WS-15 engine availability, and the political paralysis caused by the ongoing purge all suggest that readiness rates are lower than the official narrative implies. This is where Xi Jinping's anti-corruption campaign becomes strategically relevant. Rooting out corruption is necessary for long-term modernization, but in the short term, it creates hesitation. Officers avoid risk, contractors avoid commitments, and programs stall. In a conflict scenario, for example, a Taiwan contingency, honest reporting, and reliable maintenance often matter more than unproven prototypes or ambitious designs. Historical examples show that the side with transparent, realistic logistics and readiness records usually prevails. The J-36, then, is as much a story of perception as it is of engineering. Its dramatic flybys, digital renders, and viral footage create an image of overwhelming capability. It fuels think tank speculation, justifies defense budgets, and dominates online debates. Yet beneath the hype lies a set of hard realities: engines still maturing, stealth coatings difficult to maintain, political purges disrupting procurement, and a defense industrial base under scrutiny. In the end, the Sky Monster serves as a reminder that appearances in aerospace can be deceiving. China is experimenting boldly and making real technical progress. But progress does not equal readiness, and prototypes do not equal operational systems. The aircraft flying over Chengdu may look futuristic, but its ultimate impact depends on industrial capacity, organizational stability, and technical maturity, all areas currently under strain. For observers, analysts, and enthusiasts, the lesson is simple. Watch the sky, but watch the system behind it even more closely. Ambition is visible. Capability is proven. The Sky Monster captures the imagination. But the real story of China's air power is still being written. In factories, testing facilities, and procurement offices far from viral footage and media hype. The J-36 Sky Monster makes for spectacular footage and even more spectacular headlines. It captures the imagination and drives clicks. But as we've seen, an impressive flyby does not equal operational superiority. Engines are still being perfected, stealth coatings are fragile, and a major anti-corruption purge has frozen procurement and disrupted the military-industrial chain. What flies in viral footage may never reach squadrons ready for combat. The real story is less about a single aircraft and more about the system that supports it. China is experimenting boldly, testing new designs, and pushing technical boundaries. Yet ambition alone cannot overcome institutional weakness, industrial bottlenecks, and political instability. The aircraft may demonstrate what is possible in theory, but history shows that prototypes rarely survive the transition to operational reality without a mature and reliable support network. For the United States and other observers, the takeaway is clear. Air power is more than the sum of its designs. It depends on maintenance, industrial capacity, logistics, and honest reporting. In conflicts, the side that can reliably deploy, sustain, and adapt its forces almost always gains the advantage. The Sky Monster may be real, but it remains an unproven symbol rather than a game-changing weapon. So the next time a mysterious aircraft dominates headlines, remember to look beyond the viral footage. Watch the systems behind the story, the factories, the engineers, the supply chains, and the leadership that makes operational capability possible. Ambition is visible, capability is proven. And in the world of advanced military aviation, there is a huge difference between the two. If you want to stay ahead of the hype and understand the real story behind next-generation military aircraft, pay attention to the industrial and organizational realities, because that is where the true power or weakness is revealed.